So, now I'm seeing questions. To start with, could you start with a short introduction about yourself? Yeah. Hi. My name's David Grinspoon. I'm an astrobiologist. My background is in planetary science. My research focus has been on trying to understand the evolution of planetary environments with a particular interest in habitability, where we can possibly search for other places in our solar system or beyond where life could be comfortable. And more particularly, I'm interested in evolution of climates on planets like our own, or sort of like our own, and how the interactions between the surfaces and atmospheres and clouds and the sort of different parts of a planetary system, how those different elements behave with respect to one another, and how those interactions determine the long-term evolution of climate, and how planets achieve and maintain what we would consider to be habitable conditions. And of course that raises a whole host of other questions, like how the heck do we know what is habitable? What can we assume we know about life elsewhere? And so forth. I've written a couple of popular books, one on Venus called Venus Revealed, one on extraterrestrial life and its the responses it provokes in human beings, called Lonely Planets, the Natural Philosophy of Alien Life. And right now I'm sitting here in the Library of Congress because I'm here for a year. I've been appointed as the first chair of astrobiology at the Library of Congress, a new position designed to support people that are doing research on the intersection between astrobiology and wider societal questions. And my research project has to do with the Anthropocene era. Era. That was a Freudian slip. I like that, the Anthropocene era. The Anthropocene era is the term that geologists and some other people are giving to the sort of phase of Earth history defined by humans changing the planet. And so I'm trying to take a planetary science and astrobiology perspective on that. If we look at astrobiology as the relationship, as studying the relationship between planets and life, then arguably with the Anthropocene we've now entered a new stage in that relationship on Earth. So how does that look like as an event in planetary evolution, the advent of human changes on Earth, and how does that perspective illuminate our choices going into the future, and even illuminate the way we would think about the possibility of intelligent life elsewhere in the universe? Those are the questions I'm grappling with this year I've been granted here at the Library of Congress. So yeah, I'm going to make a note of that. I like the Anthropocene era. I might just have to use that. This has been very useful so far. Any answers yet? No answers. I don't really expect to. This isn't the kind of project where at the end of the year I think I'm going to have the answers. But I think what I do hope to have is a more complete and compelling description of the question, in a sense. It's a real, like astrobiology itself, I'm finding it's a real multidisciplinary effort. I'm meeting people interested in the Anthropocene coming from a background in history, philosophy, even I've been talking to some religious scholars, theologists, as well, of course, as earth scientists, planetary scientists. So a lot of what I'm doing is just searching for these connections between disciplines. Good. first to Miles' question. He says, I think the most obvious link is between the cosmos and the Anthropocene is climate change. What do you think is the second most obvious? Wow. Well, I mean, climate change is really a lot of different things, right? We can unpack that because it's not just about, I mean, the most obvious link there perhaps is, if you dissect that, is the changes in atmospheric composition that we are bringing to Earth, the Keeling curve, the increase in carbon dioxide over time, and how, in a certain sense, we are veneriforming the Earth. People talk about terraforming Mars. Well, whether we like it or not, we're veneriforming Earth now, making it more like Venus. But there are some other less obvious things where we're changing the surface reflectivity of Earth, not just by the decomposition of the polar ice shelves or the retreat of the polar ice, but by changing land use patterns, cutting down forests, desertification, and so I think if you unpack the climate change question, you find that there are really a lot of components to that. But going beyond climate change, there are a lot of I see climate change as sort of the first big challenge of the Anthropocene era, and the need to transform our energy supply of our civilization is a huge challenge. But even if we solve that, we haven't solved the fundamental dilemma of living in a sustainable way with more and more advanced technology as a global society. There are other capabilities. A big one is the promise and the peril of genetic engineering combined with nanotechnology. The ability of individuals to create very powerful agents that can transform the planet is something that will be with us long after we've solved the climate and energy problem. So there's a whole host of problems that point to the need for some better way to govern ourselves globally. And when I say govern, that freaks people out because they think I'm talking about world government. And I may not necessarily be talking about that, but we do need some global decision-making capability. Just as life can become a planetary entity, I think intelligence needs to become a planetary entity if we're going to survive these challenges. And climate, I think I'm really beginning to realize, is only the first of a whole series of challenges that requires we find a different way of doing things. Let's see. There's some other questions popping up here. If we're alone in the universe, does astrobiology and Anthropocene say something about what we might think about our responsibility as guardians of intelligent life? Well, yeah. If we're alone in the universe, really alone, then we have a much larger responsibility. As it is, I think one of the realizations of the Anthropocene that we have to become comfortable with is that we have responsibility in some sense for this planet. We didn't necessarily ask for it. We don't necessarily deserve it. But we're here and we're kind of running this place, or we've become integral into the running of it. And so that's quite a responsibility. But if we are, as Sanjoy asks, somehow actually alone, and as some people have argued, I think incorrectly, that we're really alone, then we are somehow the guardians of life and intelligence in the universe. I find that actually much more frightening than just thinking that we're in charge of this planet. If we're just in charge of this planet and there are a lot more experiments running out there, which I think is probably the case, then there's an attitude of, well, we should try our best, but if we blow it, there's plenty more where we came from. But if we're really the only ones, then, oh boy, then we really have an awesome responsibility. But fortunately, I don't think that's the case. However, it doesn't really change that much how we should approach the future, right? We have to give it our best shot. Let's see. There's some more questions written down here. Am I optimistic? Yes, I'm optimistic because why am I optimistic? I'm optimistic because I think there's a lot more that we don't know than that we do know, including about our own future and the future of the Earth. And so that gives us the choice to be optimistic or pessimistic. And I think pessimism, unwarranted pessimism, is lame and unproductive and corrosive and contagious. So as long as the range of possibilities that I logically see before us admits optimism, then I think it's a good idea to choose optimism. So that's why I'm optimistic. Let's see, what else do we got here? Can you really call climate change the first challenge of the Anthropocene? We've already had to deal with ozone depletion, acid rain, lead, and gasoline. Yeah, no, that's a very good point. That's a very, very good point, Michael W. Bush, because in a certain sense, there have been other challenges, and I think ozone is a great example because in a way you might say ozone was the first challenge of the Anthropocene, and that it was truly a global problem. Some of these other ones are not global problems, they're local problems that are wide in extent. But stratospheric ozone depletion is a global problem that we recognized and took global action to solve. And it's on its way to being solved due to those global actions. And so it's actually a wonderful example that an Anthropocene problem can be recognized and dealt with. Now, climate change, for a number of reasons, is much more tricky, but I think I'm glad you mentioned that, Michael, because it does give us a hopeful example of something that we've recognized and met. And by the way, I also have to mention that these problems, in particular the ozone problem, illustrates the power and the promise and the necessity of comparative planetology, because the reason we've learned about the ozone problem and the unintended consequences that emitting these seemingly harmless chemicals, these CFCs, chlorofluorocarbons, up into our stratosphere, the way we became aware of that problem was through studying the upper atmosphere of Venus and trying to understand why there were not more oxygen compounds, certain kind of oxygen compounds in the upper atmosphere of Venus. And then some aeronomists, the people that study the interactions of chemicals in the upper atmosphere, said, well, actually, chlorine can destroy these oxygen molecules if there's any chlorine there. And then some other alert scientists said, wait a minute, chlorine destroys oxygen molecules. Well, we're putting chlorine in the Earth's stratosphere with these CFCs, and they put two and two together, and if it had not been for those studies of the upper atmosphere of Venus, it would have been a lot longer before we realized what we were doing to Earth's stratosphere, and we would have been in a more dire condition. So there's a nice fable there. Technology. I'm reading another question now. Destructive force or saving grace of the Anthropocene era, or both? Well, definitely both. I mean, if it weren't for technology, or as Ali G calls it, technology, if it weren't for technology, then we wouldn't be in this situation, would we? But the whole point is that we are who we are. We are these creatures that invent things and discover things, and like all life, multiply globally and affect our environment in different ways. And technology has allowed us to multiply our numbers to this point where we're altering the Earth and multiply our impact, and gotten us into this mess. But we absolutely can't get out of this mess without technology. As H.G. Wells said, there is no way back into the past, our choice is the universe or nothing. We don't have the option to, I think, go back to some pre-technological Eden. We actually do have that option if we really wanted to, if we were willing to drastically reduce our numbers on Earth, by an order of magnitude, which nature may do for us. But assuming we don't choose that path, then to maintain ourselves, we have to keep technology, we have to refine technology and find a different relationship with it, and a different understanding of how we interact with the planet. And technology is going to be a huge part of that solution. So it's both the problem and the solution. Let's see. Reading another question. Sanjoy, what are your thoughts about life elsewhere in our solar system? Venus, Mars, Titan, Europa, Enceladus, Nibiru. Yeah. I don't think there's life on Nibiru. That one's easy. Okay. So Mars, first of all. I am a pessimist about life on Mars. I think Mars is the best place to look for signs of ancient life, and one of the worst places to look for present-day life. It is true that there are places on Mars, places in Mars today that may have what we consider the requirements for life as far as a microenvironment. Places where a terrestrial microbe could survive. Underground on Mars, we know there's got to be places with water, places that are protected by from the radiation by all that dirt. There's maybe some kind of flow of energy, although that might be the weak point. But Mars, to me, does not seem at all like a living planet. If you look at the Earth, Earth is flagrantly alive. The atmosphere is out of equilibrium. Every surface is covered with life. It's not subtle. The signs of life on Earth are not subtle. And I think that a planet that has had life for billions of years, as Earth has, will be flagrantly changed by a global biosphere. And Mars does not have those characteristics. Its atmosphere is stale, in equilibrium. Its surface is obviously not dominated by life. If there's life there, it's extremely subtle. And I doubt you can have a global biosphere on a planet like Mars and have it be as hidden as it seems to be. And I doubt you can have life on a planet for billions of years without it being a global biosphere. So my bias is against life on Mars today, although I'm absolutely in favor of continuing to search because, what do I know? But Mars is not the place I would look for present-day life. Mars is the place I would look for ancient life, because Mars has saved itself, its ancient self. It's remarkably well preserved, and we see many signs of a place in the past on Mars that could have been an origin of life. You mentioned Venus. I maintain a devil's advocate attachment to the possibility of life on Venus. Not on the surface, because it's hellishly hot, but in the clouds. The clouds of Venus are an aqueous environment, a watery environment, not like this, more like this, full of acid. It's an acidic environment, but it is a watery environment, and there's all kinds of energy sources and disequilibrium and chemical flows and interesting chemistry. So I maintain some hope that we could surprise ourselves by finding life in the clouds of Venus. As far as Titan, yeah, why not? Titan's got organic chemistry, it's got flows of liquid. Yeah, it's cold there, but there are liquid reservoirs and interesting chemistry going on, and we don't know enough about life to know that it must be liquid water and must be within a certain temperature range. And plus, Titan has an underground ocean. So Titan's got two chances. It's got the methane environment with all these thermodynamic transformations and organic molecules and a possibility of some exotic life, or it's also got the underground ocean, which we know occasionally gets organics mixed into it. So Titan is actually my favorite environment right now for extraterrestrial life in our solar system. Enceladus, who knows? There's water, but it doesn't seem like there's a long-term stable environment. It seems like the hot spots in the geysers probably turn on and off, and I don't know if it would be a good place to live as far as being continuously inhabitable. Europa, yeah, sure, why not? It's got water, it's got energy, it's got presumably organic. So yeah, I think we definitely need to go to Europa and melt through the ice with a submarine and search around. It's not actually a vial of acid. It's coffee, but it's fairly acidic. Believe me, the coffee here. Is Venus' atmosphere at all similar to any place on Earth where we have found life on Earth? Not on the surface. The surface of Venus is just too hot. Even for, I mean, you talk about extremophiles and how we've discovered life that can inhabit all of these different surprising environments. And it's true, the discovery of extremophiles has been important in our thinking about extraterrestrial environments because it expands the range of places where we could consider finding life. But there are some ultimate limits. The surface of Venus is so hot that organic matter of any kind is just not stable. Proteins would just denature, fly apart. I mean, that heat is just molecules bouncing against each other at incredibly high speeds, and the nature of that heat is such that a delicate, complex thing like an organic molecule doesn't stand a chance for a nanosecond. So there's no way you could have life on the surface of Venus unless you go for some really exotic possibilities. Organic life just could not exist on the surface of Venus. You'd have to go for some really exotic, silicon-based, or you're in Star Trek territory. I can't rule it out because I think we are very ignorant about life. But the place on Venus that, again, I'm drawn to is up in the air, up in the clouds, where it happens to be pretty much room temperature. We would be comfortable there if you just had an oxygen mask and maybe a Kevlar suit to keep the acid droplets off your skin. But in terms of temperature and pressure and amount of sunlight, there's a lot about the upper atmosphere or the middle atmosphere of Venus that I think is very promising. So let's see. Do you actually see Titan as a viable possibility when the water layer isn't in contact with the rock mantle? That's a good question. That's a very good question. I mean, the thing is, we know very little about, and very little is an overstatement, about the chemistry of the ocean on Titan. We know there is water, and yeah, it's true, it's not in contact with the rock mantle, and that might cause problems chemically, but it is in contact with the reservoir of organics on the surface, not necessarily continuously, but it's got to be sporadically in contact. I mean, we see cryovolcanoes, right? And so there are flows of liquid water, at least occasionally, on the surface of Titan. And there are impacts, which sometimes punch holes in that crust. And there are various geological processes that over time will mix some of that surface material into the ocean. So you do have this liquid water environment with, in a pretty unknown thermodynamic state, but with occasional admixtures of complex organics. And to me, that spells out a possible biosphere. But yeah, the point is a good one, that it's not in contact with the rock mantle, and some of the assumed chemistry that we think about for Europa has to do with the possibility of black smokers on the floor of Europa, like the black smokers on Earth's ocean, interacting directly with that ocean. And it's true. It's a good point, Michael, that you would have to, that you don't expect that on Titan. Yeah, I mean, Justin, why is the rock mantle contact important? And Michael's answered that question, that it's a question of the accessing what we call the biogenic elements. and heat supply as well. But I would maintain that we know very little of the composition of that ocean, and we know very little about the energy supply. We really don't know how fully differentiated Titan is. We know that at least at some level there will be admixtures of all these elements from, even from micrometeorites falling in from space, and the quantity of those elements in the ocean will not be zero. Whether it will be limiting is a good question, and what the energy sources will be, I just don't know. But I don't think that we can rule out life in the ocean of Titan on the basis of the absence of those kinds of interactions. Yes, the chemistry is under constraint. Very well put. Let's see, John has a question here. So much effort given to keep our probes sterile and our microbes off other planets. Has anyone given thought to actually depositing some of our extremophiles on other planets? And what are the ethics and morals of that issue? Yes. Great combination of points, John. So you've alluded at first to planetary protection. Of course, the idea that we take very seriously the ethical implications of planetary exploration and astrobiological exploration. And I'm very proud of the fact that NASA has an Office of Planetary Protection, because it's, to me, that says that NASA is in the business of applied ethics. Planetary protection is applied ethics, and we take seriously the responsibility that we don't casually contaminate other worlds, and that we certainly don't want to casually contaminate Earth with agents that could be dangerous. But having said that, it is tempting to think that we could spread life. And if one learns enough about some of these other environments to truly conclude that they are lifeless, then I think you can make an argument that the ethical imperative switches. We have an ethical imperative not to casually infect other places and inadvertently destroy a native biosphere. But I also think that, and this is maybe a little more controversial, but I think life is a good thing, and that it's part of the role of life is to spread life to more places in the universe. And so if we find completely lifeless places, then I think we would need to have some kind of a conversation about this, which is what we're doing. But I would argue that then it becomes a good thing to spread life. So first of all, we have to learn a lot more before we can even contemplate doing this. And people are contemplating it. Chris McKay wants to plant a flower on Mars, which is a beautiful idea. And I think that once we're sure we know a little bit more about Mars, and we're getting there with Mars, that let's plant flowers there and see if they'll grow. And if we've really found that we understood a place like Titan and Enceladus and these places that could possibly support life, and we really learn that they do not support life, then let's plant some seeds. Let's expand life throughout the universe. For one thing, if we do that, then we're ensuring the continued existence of Earth life. As long as Earth life is confined to one planet, then we are susceptible to a planetary disaster. And so, if we care about life, and we do, right? Then let's spread it. The analogy that some people use for the idea of spreading life to a place like Mars is like, why should we go screw up other worlds like we've screwed up our own planet? But you can also think of it as a vacant lot. If you find a vacant lot and there's nothing growing there, then why not plant a garden? So once we learn, if we really learn enough to be confident, be sure that some of these places are vacant lots, then let's plant gardens in them. So, but we're a ways off from being at that point. But what we need to do for I think at least another generation is just explore. Let's see. Given surface radiation on Mars, are you in favor of any sort of permanent colony on Mars? What could we learn having people on the surface versus rovers? Well, that's a great question. If it were just for science, if our only goal was what we could learn, then I think it's a while before we really need to send people, because for the same amount of money that we could send a few people, we could send, you know, hundreds of rovers and really and drills and explore the surface, explore the subsurface, and you know, there's an argument for people as scientific explorers, certainly, because human judgment is so critical when you get to that sort of next stage beyond just the reconnaissance stage, where actual people up there with tools and instruments could, you know, could use their heads and do a lot more kind of quick thinking and explore in a way that we don't know how to do with machines. But just for bang for the buck for science, I think we're still talking about, you know, really another generation of robotic exploration. But there are other reasons to send people other than simply scientific knowledge. And, you know, it's a whole really set of different questions, but it's sort of what we do. It's what we do as human beings. We're curious, and we want to go to new places and explore new places. I do think it's sort of our nature. I mean, a long time ago, we were only in Africa, and a courageous band of women and men left Africa and populated the earth. And I think that sooner or later, the next stage in that is going to be courageous women and men leaving Earth and living other places and exploring further. And I just think it may sound corny, but I do feel like it's part of our destiny. And people, I think people are going to do it. And the reason they're going to do it is not strictly about the maximum gain of scientific knowledge for the money. And as far as your question about radiation, that's yeah, exactly. Somebody typed here: adventure, romance, excitement. Thank you, John. That's what I'm talking about: adventure, romance, excitement. But you're right. You're right, Miles. There's a tricky problem with the radiation. The surface of Mars is somewhat deadly. I think we'll solve that problem. I mean, humans go and live places where they've got no right to be. I mean, look, like people have colonized Las Vegas. You know, there's no water there, but people have been to the moon. You know, I just think that that these are solvable problems, and it may be that the thing to do on Mars is dig a big underground shelter, and when there's a solar event, a big radiation event coming towards you, everybody gets in the shelter, and you just, you know, make sure you've got lots of good books and you know, some single malt scotch down there, and you wait it out. Or we find some other solution, but it's a technological problem. It's not an insurmountable problem, and I think it's one that we'll figure out how to solve. No more questions? Should I tell some jokes? Maybe I should ask you guys some questions. Somebody type something. I don't want to have dead air. Oh, Miles has a question. Oh, there we go. Sorry. How tough would it be to send a Curiosity equivalent to Venus? Unfortunately, pretty tough. People have come up with designs. The problem with Venus, of course, is that it's so darn hot. It's about, Fahrenheit terms, it's in the high 800s, almost 900 degrees everywhere on the surface. And the pressure is high, but that's not as big a problem. We know how to deal with pressure. It's not higher than we have technology that, you know, goes a kilometer deep in the ocean. We know how to deal with pressure, but the temperature is very tricky. We don't really know how to design electronics and computer memories and transmitters that work at those temperatures, and so therefore people talk about designing big refrigerators, nuclear-powered refrigerators that are rather inelegant, and we actually have designs to do that, but they're big and bulky and costly. I think ultimately it will be we will ultimately learn how to actually develop electronics and develop instrumentation that actually functions comfortably in those conditions, rather than having to surround something in a shell of Earth-like conditions. But you know, a rover, a Curiosity-type rover, is not the next step for Venus. Somebody mentioned weather balloons, and yeah, balloons we know how to do is not a huge technological challenge. And I think surface missions to Venus are important, but probably not rovers. Even just landers that could last for a few hours. You know, the Russians had Venus landers that lasted for an hour or so, but that was 20 years ago, and we didn't have the instrumentation and the knowledge to ask the right questions. If we had a Venus lander now, a couple of Venus landers in well-chosen places, given that we now have global maps and we know the interesting places, and we have better instruments so we know how to probe those rocks, and we could really learn a lot about the history of that planet and the history of the climate and the past existence of oceans on Venus. So I think just Venus landers would be very important. And entry probes to really explore the lower atmosphere with drop probes that don't have to last long. They just have to have good instrumentation and send the information back. Balloons. And the other thing is there's a lot more we can do with sophisticated Venus orbiters that we haven't done with radar interferometry, really better surface mapping. Now we know that there are probably active volcanoes on Venus. We can nail that down and really find the active volcanoes with new generation of orbiter instruments that we haven't had. So I would love to see rovers or some kind of mobility, maybe the other idea is low altitude aerial platforms on Venus eventually. I mean, definitely we have to do that eventually, but I don't see it as the next step for Venus. Was there a touch-and-go lander balloon hybrid Venus design? Yeah. That's right. So there's also this idea of a platform for Venus that could touch down briefly in a place, do sampling, do observations, and then before it gets too hot, go back up into high enough in the atmosphere, 20 kilometers up or so, float around in the global winds until you get to another interesting place and then go down again. In fact, people have designed these sort of selectively buoyant balloons that have some kind of a bellows or some kind of a phase change material that you heat and cool, and the density increases and decreases, so you can make the thing float up, and then you float around the winds, and then you go back down to the surface and do more experiments. So yeah, there are ideas for platforms on Venus where you could have some kind of mobility and do some kind of surface science without having to solve the really tricky problem of how to survive there for hours or days or months. You know, eventually you want really long-term platforms on Venus because one of the most interesting things you want to do eventually is seismology. Probe the interior of Venus. It's the only other Earth-sized planet we can do seismology on. And it's a fascinating comparison with Earth because it is the same size almost. And so it ought to have an interior structure that's similar to Earth's, an interior dynamic similar to Earth's. And yet we know it's been wrung dry and it's desiccated, and so the interior properties are a little bit different. So if we could do seismology on Venus and really understand its interior, we'd learn a lot more about that coupled history of the interior, the surface, the atmosphere, and we'd actually learn a lot more about Earth by being able to do seismology on Venus. But in order to do that, you really need a long-lived surface platform, and that's not going to be easy. Let's see. Any other questions? Have I missed any? I seem to remember you are certified for suborbital flight. Is that right? How does that work? Yeah, I am certified for suborbital flight. There was a class a couple years ago now that was organized to train a group of scientists to be suborbital astronauts. And I was among that first dozen. And I found out that I at least have enough of the right stuff so that I did not throw up on the centrifuge when we went up to 6G. So that was good to know. It was actually challenging and a lot of fun. And the next step is for the suborbital flights to start up. You know, there are all these companies, Virgin Galactic and these other competing companies that are getting ready to start sending people into space on suborbital flights. And the idea is that rather than have it just be for rich tourists, let's have a research and education component on the suborbital flights. And in some ways, they're really good research platforms and really good education platforms. And it's been gratifying to see that the consortium of companies preparing to do these flights has been very opening to broadening the mission beyond just tourism and having a research and education mission associated with these. So that is happening, and a lot of us who are trained are just kind of waiting for these flights to get going. And yeah, I would love to go up. And what I would love to do is some kind of educational project where, for instance, I can imagine being up there in space in weightlessness and talking like this, but to a classroom or an auditorium or many auditoriums full of kids, and have some kind of two-way conversation, and be like, "Whoa, I'm in space," and they would, ask me questions about what it feels like and what I could see, and have some kind of a two-way conversation and sort of share the experience, and hopefully inspire curiosity and spark some young minds. So that's one thing I would really love to do. Let's see. I see some questions popping up here. Let's see. What do we need to do to learn more about exoplanets? And how important are exoplanets? Well, they're hugely important. I mean, this is a revolution in knowledge happening right now that's, equal to any revolution, I think, in human knowledge. It's actually absolutely huge. The idea that there are other planets out there is one that scientists have long kind of assumed or thought was reasonable. When I was in grad school in the 80s, we didn't know about exoplanets, but we learned about the formation of the solar system as kind of a natural byproduct of the formation of our star. The stuff that's left over from forming the star coagulates and accretes into planets, and that ought to happen elsewhere. So we kind of assumed for a long time they were out there, but it was a weird kind of scientific faith, a belief that wasn't really supported by evidence, or at least it was only supported by inductive logic. And now, of course, we've started to find them, and we're finding that they are, as a lot of us suspected, commonplace, that when you look up in the sky at night, a sky full of stars, you know now that most of those stars have planets orbiting them. So that's a huge change in what we really know about the universe. And you can look at this progression in history of things that we sort of assumed and now we know. Going back even to the 1600s, some people assumed that the stars might be suns, and then we discovered, yes, the stars really are suns. And then we kind of assumed, well, if they're suns, they probably all have planets around them. And then we discovered, actually, that's true. They do all have planets around them. Well, now we still have this assumption some portion of those planets probably have life on them. And that's still something that is a kind of faith. It's a kind of scientific faith. By inductive logic, a lot of us assume it must be true, but we don't have the evidence. So can we move that from this assumed belief column into the observed fact, a known fact column? I think we will, but obviously an important step along that direction is the discovery of the exoplanets. Now, as far as how can we learn more about them, it seems crazy that we could learn very much about them. They're so darn far away. We don't even know about them for the most part by even seeing them directly. We infer their existence indirectly by the way they move around their companion star. And yet, amazingly, we've started to learn a lot about some of these exoplanets. And I'm just blown away by the creativity and the imagination and the ingenuity of this generation now of mostly young scientists that are making it their career to learn something about the exoplanets and doing these very clever observations of, when a planet passes in front of a star, how does the spectrum of the light change? what is being subtracted and added to that spectrum by the surface or the gases on that planet. You know, a lot of very clever techniques looking at these very, very subtle effects. But the progress that's been made already in just the first real decade, I'd say, of exoplanet observations, without even having instruments that are optimized for that, using instruments that were built for other things, is really encouraging and inspiring. And what's going to happen now is that we're going to build new instruments, new space telescopes that are really designed for the purpose of learning about these exoplanets, and we're going to start to learn what their atmospheres are made out of, how reflective their surfaces are, how their reflectivity changes as they rotate, which tells us something about whether they have continents and oceans, and you know, whether we can see the glint of oceans reflecting off them. And people are just going to keep coming up with these very clever ways of learning new things about exoplanets, some of which we haven't even thought of yet at all. And so the direction, you know, the arc of exoplanet science is long, but it bends towards knowledge. Sorry to bastardize Martin Luther King there, but you know, this is the way things are going, and so we're going to learn a lot about these places, and sooner or later we're going to discover one that's got such a weird atmosphere that it's telling us that there's probably something living there. Which feeds into this question: what sorts of things should we or could we look for to see evidence of other biospheres on exoplanets? How hard is it to see those things? Well, again, it's hard, but the signs are encouraging. The fact that people are learning to do these very clever observations, and a great way to look for life on an exoplanet is to look for a really weird atmosphere. I mean, what's the one planet we know of with life? Earth. And what's the planet with the weirdest atmosphere? You know, it's Earth. I mean, look at our neighbor planets. Venus, all CO2, a little bit of this, a little bit of that, but basically all CO2. Mars, all CO2, a little bit of this, a little bit of that, basically all CO2. And then you look at Earth and you go, whoa, wait a minute, there's something weird about that planet. What's all this oxygen? And there's even methane mixed in with that oxygen. That shouldn't be there because methane reacts with oxygen. Something is happening on that planet maintaining this strange atmosphere. That something is life. And I think that finding flagrantly anomalous atmospheres is right now is our best shot of finding a biosphere on an exoplanet. And I don't think ultimately it's going to be that hard if we build the right instruments and keep going with this amazing effort to extract information from the small number of photons of light that we're capturing from these worlds. Have you read about any Venus-like extrasolar planets, and how excited are you to study their data? Well, yeah, I mean, you know, we don't know enough about very many of these exoplanets to be sure that there are any that are Venus-like. But I wouldn't be surprised, because I think Venus-like planets are probably common in the universe. I mean, CO2-dominated atmospheres are going to be common. CO2 is just, you know, it's one of the things planets do when they have rocks and they make volcanoes and they put CO2 into the atmosphere. So it's almost like the normal state of an Earth-like atmosphere is CO2, and a certain number of those planets are going to be on what we call the inner edge of the habitable zone, or inside the habitable zone, where they're hot enough so that they lose their water in a runaway greenhouse, which is what happened to Venus. And so I think that the Venus-like state of terrestrial planets will be common. And so I think we will find Venus-like extrasolar planets. I wouldn't say that we've discovered any yet that are dead ringers for Venus, but I mean, this is in its infancy, and we may have. We just don't know enough about them to be able to say that. And I think it would be really exciting to study them. I mean, the fact that there's this diversity of planets coming down the pike, so that, you know, in the terrestrial planet game, we've basically had three planets to study: Earth, Venus, and Mars. And it's been very fruitful, that comparison, but it's a very limited data set. And now there are going to be hundreds coming down the pike, and we'll really get to characterize and see how weird Venus, Earth, and Mars, and how they fit into a wider spectrum. So it's something to look forward to. Okay, time for one or two more questions. Do you think we will more likely discover life via atmospheric detection or evidence of technology, aka radio waves or the like, on exoplanets? Ha ha ha. Ah. Um. Gosh, that's just such a hard question. Um, I don't know. I think that it's incumbent upon us to search for life in any way we can, which means exploring our own solar system more fully to really know if there's anything weird going on Titan or these other places we've talked about, to look for anomalous signatures in the atmospheres of exoplanets. Of course, we have to continue our SETI searches by looking for radio waves or artifacts or astroengineering. You know, we just don't know. We're ignorant, and we have to keep searching. If I had to put money on it, which I don't, fortunately, but if I had to, I would say that the most promising possibility is finding an exoplanet with a truly anomalous atmosphere that just cries out life. Because that's something that we know is coming down the pike. We know that before too long we're going to build these instruments and we're going to have good atmospheric signatures for, you know, dozens, hundreds of exoplanets. And so if life planets are not extraordinarily rare, then we'll start to find them, right? But there's always wildcard discoveries that could happen in SETI. Seth Shostak points out that SETI searches are becoming sort of exponentially more powerful, and therefore he predicts that SETI search will have success in the next 20 years. Maybe he's right. It's certainly worth continuing to search for that long and a lot longer. Do you have any input into the atmospheric detection instrumentation? Yeah, I don't. Well, I mean, I sit on committees that make recommendations. So in a broad sense, I have input. I am not personally an instrument builder. That's not what I do. So I'm not the person with the most input, but I know what I like. When I get asked to sit on committees, you know, I try to point out things that I think would be useful. Doesn't it seem logical that life on some planet somewhere in the universe is facing the same type of Anthropocene challenges we are seeing on Earth? Yeah, I think so. I mean, that's one of the things I'm trying to do with my work here at the library, is look at the Anthropocene from this lens of, okay, what is really going on here from a planetary transition point of view? How can we abstract this? And I think that a planet with life will become a global phenomenon, and a planet that develops complex life is likely to develop, you know, intelligence, and we could talk about what that means, but because cognitive abilities are a big survival boost. And the niche that human beings have filled on Earth with these flexible brains and being social creatures with flexible brains able to solve problems and create technology seems like a niche that will evolve under selective pressure on other planets. Once you have that niche and life is becoming technological, then I think it's only a matter of time before they have this sort of Anthropocene moment or their own local equivalent that we're having now, and realize that, oh, we're affecting our environment globally in ways that may not facilitate our long-term survival unless we start to think of ourselves as a global entity and change the way we do things. That's the moment we are at. And yes, I do think it's likely that would happen elsewhere, and how life responds to that challenge will be what determines the longevity of life and intelligence on that planet. And thus, any intelligent life we find elsewhere, I think, will surely have reached this moment and somehow gotten through it. And so, for one thing, if we find extraterrestrial intelligence, I think it shows that Anthropocene error, that challenge that we are facing now, is a solvable problem. And so, in that overall sense, I think it would be a very hopeful thing to discover. How are we doing, Sanjoy? Are we? That almost seems like a final point, but Shadows of Percival Lowell. Well, yeah. The thing about Percival Lowell is that he was the first guy to do comparative planetology, right? And so we diss his specifics, and he came up with some loopy stuff, but he also got us thinking along the lines that we need to be thinking in terms of comparative planetology. So let's not completely diss Percival. Hey, thank you so much, Sanjoy, for arranging this, and thank you all for participating. It's been really fun for me, and thank you all so much for the great questions. Let's do it again sometime. You're all invited over to Sanjoy's house now for beer. Hey, Batul. Thank you. Thanks, everybody. Everybody howl and hoot. Oh, beer's on Thursday. All right. He'll post the address later. All right. I guess we're gonna sign off then, right? All right. Take care, everybody. It's been really fun.